Okay, so this is a review guide for the waves and sound test. I got the multiple choice here, a couple practice problems, and then again, you've got your reading guides. The multiple choice from the actual test will come from the reading guide. These are just kind of practice versions of that. So, the time needed for a wave to make one complete cycle. So that's to travel one wavelength or go up and down or back and forth if it's longitudinal. The time needed is called the period. The rate at which it does it, the opposite of period, is called frequency, but the time needed for one cycle is called period. So is it two sound waves passing through the same medium have different wavelengths. So same velocity, because it's the same medium. Anytime you see the word same medium, you're going to think same velocity. That's why we do that. And remember, velocity equals wavelength times frequency. So if it's the same velocity, you change one of these, the other changes. Have different wavelengths. Which of the following is most likely to be the reason for the differing wavelengths? Nature of the medium, differences in amplitude, differences in frequency, type of the wave. Well, nope, none of those are going to change it except frequency. Same medium, different wavelengths. The wavelength is different because the frequency changes. Two waves traveling in opposite directions on a rope meet and undergo complete destructive interference, which means the up cancels the down. Which of the following best describes the waves a moment after the waves meet and coincide? So this is after they've done that and they continue on. Waves no longer exist. Nope. Energy's still there. Continue unchanged. That sounds good. Waves reflect and travel backwards. Nope, they don't bounce off each other, and they definitely don't turn into one wave. It's B. They continue on unchanged. Which of the following interference will occur when the pulses? So you've got an up and I've got a down. We should have destructive interference. So it's not complete destructive because it'll still be some wave left. So we're going to call that partial destructive. A 3-meter long stretched string is fixed at both ends. So I've got 3 meters long. How many nodes will be formed for the third mode? So if we want to draw that on there, you got 1, 2, 3 humps. And so then it's how many nodes? So we're looking at 1, 2, 3, 4 nodes. Make sure you can do this not just in a multiple choice, but in a actual problem style as well. Sound waves are a part of the electromagnetic spectrum. Nope, that's light and radio waves and microwaves. Do not require a medium. Nope, sound definitely requires a medium, whether it's solid, liquid, or gas. Longitudinal, sound is longitudinal and transverse. Nope, they're not transverse, they're longitudinal waves. Sound waves are longitudinal. Which of the following is a region of a sound wave in which the density and pressure are greater? So you have high density, high pressure. And again, you have that compression, rarefaction, and these are kind of moving back and forth, the particles. And so this is between the rarefaction and the compression. The compression is the higher density. Rarefaction is the lower density, or lower pressure. In general, sound travels faster through solids than through gases. It definitely travels faster in solids than gases. Gases than solids, nope. Gases than liquids, nope. Faster in liquids than gases. Empty space, can't travel here, so it's A. Sound travels fastest in A, solids. Train moves down the track towards an observer. So we've got a train moving this way, and here's the observer. As heard by the observer, so what sound is this guy here? Is blank the sound heard by the passenger on the train. So the passenger on the train is going to hear the same sound as the train's producing. So that would be the same, A. But the observer is going to hear a scrunched up wave versus a stretched out wave. So it's going to hear a higher frequency. And so we want to hear higher pitch. Pitch and frequency are the same thing. So higher in pitch, C. Doppler effect occurs when only sound waves. Nope. Transverse wave, yep, occurs here. Not only sound waves, it happens with light, it happens with water. Remember the duck happens with, can't happen with slinkies. Only water waves? Nope, all waves, D. Happens with all waves. When the frequency of a force is applied to an object that matches the frequency of vibration, so you can think of the swing, pushing the swing at certain intervals, right? The pendulum, pushing at the right time will add energy to it. Same thing happens with your wave. If you increase the wave each time, we end up with this thing called resonance. Resonance is when you add energy at a specific frequency, or force is applied at a specific frequency, D. All right, some math problems. Pendulum. Grandfather clock swings back and forth 180 times in 6 minutes. So we're looking at N, number of times is 180, and 6 minutes is our time, but that's not in seconds. We need that in seconds, so it'll be 6 times 60, which will be 360 seconds. All right, what is the period? T is the total time over the number. In this case, it's 360 divided by 180, or 2 seconds. Nope. Did I do that right? Yeah, I did that right. 2 seconds per oscillation. 180 oscillations, 6 minutes, so 2 seconds. And then the frequency is just 1 over the period, or you could just flip these and do N over T, but I'm going to do it this way. So I'll say 1 over 2, or 0.5 hertz. All right, radio waves from an FM station have a frequency of 103.1. Here's the speed. What's the wavelength? Well, velocity equals frequency times wavelength. 3 times 10 to the 8th equals the frequency, 103.1 times 10 to the 6th. Again, mega is times 10 to the 6th. So I just replace that M with times 10 to the 6th. You don't need to worry about the decimal. The calculator will handle that. And I solve for the wavelength. And I need a calculator with scientific notation. You have 3E8 divided by 103.1 E6, and you get a wavelength of 2.91 meters. All right, so relationship between frequency and wavelength. Make sure you can do this type of problem, maybe not this specific, but if you know the wavelength and the speed of a wave, speed and wavelength, find frequency, or if you know the speed and the frequency, find wavelength. All right, vibration of a certain frequency produces a standing wave on a stretched string that is 2 meters long. So again, let's draw the 2 meter wave. So 2 meters long, that's L, length. Standing wave has 7 nodes and 6 antinodes. So that means 6 humps. So we're going to go 1, 2, 3, 4, 5, 6. So 6 antinodes, and then we've got 1, 2, 3, 4, 5, 6, 7 nodes. So yep, that's it. Now, what is the wavelength of this wave that produces this standing wave? So what is the wavelength of this wave? Well, remember from the lab, wavelength is equal to the length over the number of waves. This is from the lab. We use this in the lab. Make sure you can do it on the test. All right, so 2 meter long, that's my length. What is the wavelength of this wave? Well, I've got 1 wave. So here, let's draw 1 wave, 2 waves, 3 waves. I've got exactly 3 waves. So my wavelength will be 2 meters divided by 3, or 0.667 meters. And there's my wavelength. All right, reflection. Following pulse, oh, there's that triangle, sent down a slinky. Draw the resulting waves if it hits a fixed end. So if it hits a fixed end, it's going to come back. Fixed end means flipped, so it's going to flip over to the other side, and the leading side needs to stay the leading side. And so we'll go, we'll draw it this way. Good. Draw the resulting of a loose end. All right, so if it hits a loose end, it's going to come back the other way. It's not going to flip. It's not going to flip, but the leading side will still stay the leading side, so it'll be up on top still. All right, it's a more dense slinky. So we've got a light, and we're going to put some sort of wave there into a more dense, and I'm going to leave a blank there where we can put a wave. All right, so we're going, hits a more dense. So we're going, this right here is the light one going into this. It's going to hit this boundary here, and it's going to bounce back, and it's going to transmit. So let's draw what it looks like. Well, transmit's always the easiest. So it always transmits on the same side. So if it's on the top coming in, it's going to be on the top as it transmits. So there's that part. And then next is, well, does it flip or does it not flip when it reflects back? because remember, it does both off of this boundary. Well, if it goes from light to heavy, you said the rule was that it flips. It acts as a fixed end. So it's going to be on the bottom. And there you go. Well, if it hits a less dense slinky, so now we're saying this is the heavy slinky or heavy string, and it hits a lighter one. So again, let's set up our drawing. There's our wave. We're going to have a pulse there, and then we'll have another pulse there. So again, this is going to go from the heavy, so it's coming in this way, and it's going to continue and reflect. So first, transmit. Always transmits the same side, so since it's on the top here, it'll be on the top here. Very good. Make sure you can see that that's the front edge. And then how does it reflect? Well, since it's going from a heavy to light, it's going to act as a loose end or same side, so it'll be up on top over here. Doesn't flip to the other side. And there you go. All right, last page. This is kind of a standing wave, so think back to that standing wave lab, although I have given you the velocity. So again, you see velocity of a wave. I tell you the velocity of a wave, you really should be thinking velocity equals frequency times wavelength. Have that in the back of your mind. We're probably going to use that at some point. Anyway, and the string is 0.3 meters long. So draw the first and third harmonics, labeling all the nodes and antinodes. So the first harmonic, again, I like to draw it out kind of like this. This is 0.33 meters. So this is my length is 0.33 meters. I may use that in a calculation later, but right now, draw the first. So the first harmonic has a single hump, and I always put the other side on it. And we'll have antinode in the middle, and again, it's this whole spot. It's not the top, it's not the bottom, it's this location side to side. And we have the two nodes there and there. All right, all the nodes and antinodes. So then we have, what is the first and third harmonic? Again, third harmonic, same string. I drew it a little longer, it's gonna be easier, but that's okay. One hump, two hump, three hump. All right, and then we'll draw the opposites. And so antinode here, here, and here. Again, it's this whole location. You could put them on the bottom, the top, the middle, wherever you want to label it. And then I've got a node, a node, a node, and a node. Here, here, really it should be up a little bit, here, and here. All right, calculate the wavelength of the first mode. So we're looking at here. And then again, wavelength is equal to the length of the string divided by the number of waves. Well, in this case, it's 0.33 meters, so 0.33. A violin is not very long. 0.33 meters divided by the number of waves in this first mode is half a wavelength. Full wavelength would keep going, but again, it reflects back, and that's why you get the constructive and destructive interference. 0.5, and so we end up with 0.66 meters, wavelength of first mode. What is the frequency of the first mode? Well, velocity, I told you we're going to be using that equation. Velocity equals frequency times wavelength. I know the wavelength, I know the velocity from here, so I can say 884 equals the frequency, what I'm trying to find, times the wavelength. Grab my little calculator, 884 divided by 0.66, and I get a frequency make sure I did this right. Yep, sorry. Frequency of 1,339.4 hertz. So there's my frequency. Now, what is the frequency of the third mode? Two ways you can do this. I'm going to do the way, redo BC, except do it for this one over here. So I'll say wavelength equals length over number. In this case, it's 0.33 over, now I have 1.5 waves, so 1.5, and I get a wavelength of 0.33 divided by 1.5, so a much smaller wavelength. And then I can use my velocity equals frequency times wavelength equation again, 4 is frequency times my new wavelength. And so I'll just say 884 divided by 0.22, and I get a large frequency, larger because it's a higher, it has to go faster for that next mode, 4,018 hertz. That's one way. Or you can recognize the pattern that each mode is a multiple of the first mode. So if I want mode 1 was 1,339.4 hertz, well, mode 2 would be 2 times this. Would be 2,678.8 hertz. All right, and you should have probably noticed this pattern at some point during that lab when you did with the standing wave. And again, the third mode, I would take this first mode and multiply it times 3. 1,339.4 times 3. And I get 4,018.2. 4,018, there it is, the same number. So, if you wanted to just say 3 times 1,339.4, because you're going from the first to the third mode, you could do that. Right, which is where that number comes from. So, either way works, whichever one makes sense to you.